Hello! Let's take a look to our usual surrounding. Imagine everything around us, but just as it was 30 years ago, in the 80s. I don't know, you weren't born. But anyway, it is an interesting thought. Just stop to think what things we could have and what we couldn't in our daily life. Cars? Of course there were cars, but they haven't got an airbag or a GPS navigation system. Telephones? Of course there were telephones, but the only way to use a telephone while walking along the street was finding a cabin connected by wires to the network. Music replicators or players? Of course there were some of them too, but the only way to hear music on the go was using Walkmans. Or you could even find big radio cassette players lifted on the shoulder as parrots. TVs? Of course there were TVs, based on cathode ray tubes, receiving analog signals through antennas and wires. Let's ask ourselves a question. What is the reason of this overwhelming change? What could motivate the change of such many things in such a short time? By poring over the matter and finding the answers, one bump into the electronics. Both analog and digital electronics. Parts are becoming smaller and smaller because of semiconductor materials. Mainly, the fact of making extremely small devices and extremely efficient in their purposes has outreached the miniaturization of the electronic systems once and again. The simplest cellular that you can find nowadays in the market has got more electronics inside than the probes sent by the humankind that are currently reaching our solar system limits.
Along this video collection, we will discover analog electronics from square one,
starting from its roots, the semiconductor materials. The whole tree of the classic electronic devices will be described. We will also introduce some practical ideas and methods of the laboratory stuff, just for increasing your skills for it. Specifically, we will show in this video that what the semiconductor materials are and what is there inside.
A piece of polycrystalline material after its transformation as ingot and then as a wafer, as we saw in the fundamentals of electronic engineering course, allows the creation of the devices that we will study. Here we are the differences between an electrical conductor, an insulator, and a semiconductor material. An electrical conductor is a material with free electrons in its atomic network, into which there are metallic bonds linking the atoms. Free electrons are carriers of charge, and the electrical conduction is made by them. An insulator, on the contrary, has got atoms in covalent bonds sharing their electrons at their last layers and avoiding the existence of free electrons. Any charge is moving from one side to another. A semiconductor is an intermediate state, conducting when some electrons get free from their atomic bonds. Let's see the energy diagram. There is a huge gap between the valence and conduction band for the electrons in an insulator. In a semiconductor, it is smaller. So, in a conductor material, there is no gap at all. Both bands are overlapped. Let's explore an intrinsic semiconductor, as for instance, the silicon. Here, we can see the atomic layout of the silicon structure. Tetrahedral bonds geometry due to the shading of the electrons in the last atomic layer. Please, let me explain it in a plane, not in a three-dimensional. If we have got a silicon atom with a nucleus in the middle and a set of atomic layers completed and filled with electrons, all of that being this orange ball here, the last atomic layer has got 4 electrons. Anyway, to be completed, this layer needs 4 more electrons to be fulfilled. The way nature follows to get this is shading electrons with the atoms in the neighborhood, being then every silicon atom surrounded by another 4. For instance, this central atom is shading electrons with the 4 atoms surrounding it. Well, let's focus for a while in one electron. By the simple fact of having this material at a certain temperature, it is to say, in some energy condition over the 0 Kelvin, vibrations into the system may make this electron to get free from its weak bond. Then the electron is free to move, and there is a sudden appearance of the absence of that electron in that particular bond. This is called a hole, and as we will see, its behavior is very similar to a positive charge. In fact, electrons and holes are behaving as charge carriers. Both are then called so, carriers. We have described the process named an electron-hole pair generation. The contrary process, a free electron filling a hole and linking to a bond, is called recombination. We will name N to the electron concentration and P to the hole concentration, or population. In an intrinsic semiconductor at a certain temperature, N is equal to P. By the way, we will call N to any material with electrons as majority carriers, and P to the one with holes. Suppose for a while that we increase the temperature. Then the energetic condition of the material is increasing too. Then more and more electrons may free from their bonds, and then the concentration of carrier increases. Summing up, by increasing the temperature, a generation of more and more free carriers is produced. An electron moves energetically from valence to conduction band by an electron-hole pair generation. In thermal equilibrium, generation and recombination of pairs are two balanced processes in an intrinsic semiconductor. Now let's take a look to an extrinsic semiconductor, that one doped with a different element. First, in the periodic chart of elements, we notice that silicon is in the same column as carbon or germanium. They are semiconductors. Also, combinations between elements of columns 13th and 15th, like gallium arsenide, for instance. If we dope with atoms of elements from 13th or 15th column to a silicon network, we will get an extrinsic semiconductor. Please notice that those columns stand for atoms with 3 or 5 electrons at their last layer, respectively. It is one more or one less than the one of silicon. Let's begin with the N-type silicon. By diffusion, some phosphorus atoms, for instance, can make their own room among the silicon atoms and their network. Then, 4 of the 5 electrons at the last layer of the phosphorus atom make covalent bonds with silicon atoms surrounding it, but the 5th one is not bonded, and it can easily be freed to move along the material. Now there is a new electron with no associated hole behind. Then an N-type semiconductor has got some free electrons moving in the network. Focusing in the phosphorus atom, its atomic number means that it should have 5 electrons in its final layer, but in fact it has got 4 now. Technically, it has become a positive ion anchored to the silicon network with no movement. So we can visualize the N-type semiconductor as a semiconductor network where free charge carrier pairs are continually generated by temperature. Not interesting, a set of free electrons with no hole associated, free charge and paired carriers that can conduct an electrical current, and a set of the same number of positive ions anchored to the semiconductor network. This is the way to represent that. In a P-type silicon, the idea is the same, but inserting among its network an element on the left at a periodic chart, for instance, boron. This one has got only 3 electrons in its last layer. One of its bonds is electron empty. In fact, it behaves as a hole. A closed electron might recombine with it, leaving another hole behind him. The process of electron-hole pair recombination can be repeated constantly. Technically speaking, is the same as if we could say the hole is moving along the material. Then we can assume that the p-type semiconductor consists of a semiconductor network where free charge barrier pairs are continually generated by temperature. Not interesting, this is represented by the orange layer here. A set of free holes with no associated electron as free charge and pair carriers that can conduct an electrical positive current. Here it is. And a set of the same number of negative ions anchored to the semiconductor network. Summing up, an extrinsic semiconductor is that one doped with other elements that can generate a set of free charge carriers. The inserted atoms of the new element produce holes in a p-type semiconductor and electrons in an n-type semiconductor. The holes are produced by acceptor atoms and the electrons by donor atoms. The majority carriers in an extrinsic n-type semiconductor are electrons in a p-type 1 hole. We are going to speak about the carrier conduction mechanisms. Mainly there are two, diffusion and drift. Regarding diffusion, let's imagine a bulk of semiconductor, N or p-type, which has got a lot of carriers inside. Imagine that just after the diffusion of the corresponding atoms here, there are a lot of free carriers in one area near the interface of the air and the wafer, this one. These free charge carriers share the same charge, all of them, positive or negative, but the same. Then, by simple electrical reaction, they tend to move away each other, filling the area on the right side of the drawn bulk material. We are seeing a diffusion current, and we have discovered that this is caused by a gradient in the concentration of carriers. Let's take a look to the conduction or drift current. From an initial semiconductor, as the ones that we have seen, we add a strong electrical field from left to right. Electrons are then impelled to move backwards from right to left. Here it is. As we have seen, any other electron may move in the same way as long as there are holes created on its vicinity. Technically, a current is created of electrons moving from right to left, and or a current of holes moving from left to right. As we see, holes are behaving exactly like positive charges do. That is the reason to treat them in that way. So a drift current is produced under an electrical field. See you in the next video.